Chapter 3, Section 3.1. In 2.4, we define the slope of a curve y equals f of x at the point where x equals a to be m equals the limit as h approaches 0 of f of a plus h minus f of a all over h. When the slope exists, it is called the derivative of f at a. Okay, the derivative of f can also be called the instantaneous rate of change of f, can also be called the slope of the tangent to the curve of f, and can also be called the slope of the curve f. There are a few notation things for derivative. So we have f with an apostrophe of f of x, which is read f prime. So the prime is the apostrophe of x. We can also have y with an apostrophe, which is read y prime. And then we also have dy dx, which is read dy dx. And then we can also have d over dx of f of x, which is read df of x dx. These two notation come from the change in y over change in x that we know about slope. So the definition of derivative. The derivative of a function with f with respect to the variable x is the function f prime whose value at x is the limit as h approaches 0 of f of a plus h minus f of a all over h, provided that the limit exists. So note, if f prime exists, we say that f has a derivative or is differentiable at x. A function that is differentiable at every point of its domain is a differentiable function. At the bottom of each page in this note sheet, you will see this little check-in. So the objective of the notes is that you'll be able to define derivative and use accurate notation, identify relationships between graphs of f and f prime, while also graphing derivative from data, and also find one-sided limit. So as you go through these notes, at the bottom of each page you will circle either met it, on track, or on a different train for each topic on the page. Moving on to page 2. Applying the definition. So we want to differentiate or find the derivative of f of x equals x cubed. So the first thing that we want to do is set up our derivative equation. So we have f prime of x equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, which is equal to x plus h cubed minus x cubed all over h, which is equal to x cubed plus 3x squared h plus 3x h squared plus h squared that should be cubed minus x cubed all over h. This leads to limit as h approaches 0 of 3x squared plus 3xh h squared times h, because we can pull out an h once we cancel out these two x cubes, all over h. So the limit as h approaches 0, the h's will cancel, 3x squared plus 3xh plus h squared is equal to 3x squared. So that was just one example problem. If you feel like you need a little bit more practice on these types of problems, exercises 1 through 4 on page 105 of your textbook has a few more that you can use for your own practice. The next thing we want to talk about is the derivative at a point. So the derivative of a function f at point x equals a is the limit. So the derivative of f prime of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a, provided that the limit exists. So this should still look very similar to what we have been doing, right? Change in y over change in x. We're finding the limit as x approaches that value a. So we want to differentiate f of x equaling square root of x at the point x equals a. So we will use the equation above, which was prime of a equals the limit as x approaches a of f of x minus f of a all over x minus a. And then we have that equal to the limit as x approaches a of f of x, which is square root of x, minus f of a, which is square root of a, all over x minus a. So if we were to try to directly substitute into this equation, we would get 0 over 0, so we want to rationalize the top and the bottom by multiplying by square root of x plus square root of a. And we'll get the limit x approaches a of x minus a on top and x minus a square root of x plus square root of a. The x minus a's will cancel, and we'll get the limit as x approaches a of 1 over square root x plus square root a. And now we can directly substitute, and we will get the limit x approaches a f of x as f of a over x minus a is equal to 1 over 2 square root of a. So again, if you need some more practice on this type of problem, you can refer to questions 5 through 8 on page 105 of your textbook. So down at the bottom, I'd like you to take a couple seconds and just circle where you feel you are based on our objectives. Do you feel like you're on track, or do you feel like you're on a different train? You cannot circle met it because we are not quite done with the notes, so you have not yet met every single objective. But are you on track, or are you on a different train? If you feel like you're on a different train, try a few more practice problems out of the book to help you out. Into page 3. Okay, so now we're going to be graphing some f prime and f graphs. So in order to graph f prime, so this would be the derivative from the original, we need to know what the slope is for each section of this original graph. So the slope here from -2 to negative 1. Our graph is going up 1 over 1. So the slope here is positive 1. The slope from negative 1 to 0 is up 2 over 1. So positive 2. The slope from 0 to 2 is up 1 over 2. So our slope is 1/2. The slope from 2 to 3 is down 3 over 1, so our slope is negative 3 over 1. And then lastly, our slope from 3 to 4 is down 1 over 1, so our slope is negative 1. So in order to transfer that onto this graph, we know that from negative 2 to negative 1, our graph's slope was 1. So we have a graph that is moving at a slope of 1. So remember, the graph of the derivative is the graph of slopes. So our graph is moving at a slope of 1 from negative 2 to negative 1. Then it is moving at a slope of 2 from negative 1 to 0. Then it is moving at a slope of 1/2 from 0 to 2. So from 0 to 2, our slope is 1/2. Then it is moving at a slope of negative 3 from 2 to 3. And then lastly, it's moving at a slope of negative 1 from 3 to 4. So this is our derivative graph as a graph of the slopes of the original. So if you'd like more practice on going from original to derivative, please look at exercises 13 through 16 and 26 on pages 105 and 107 of your textbook. So now going backwards, from f prime of x to f of x, if f of x is a continuous function and f of 0 is equal to 0, so we know that f of 0 is equal to 0, it's important, we want to sketch the graph of f of x. So our f prime has a slope of 2 from negative 4 to negative 1. So our graph has a slope of 2 from negative 4 to negative 1. Then it also has a slope of 1 from negative 1 to negative 2. And we know that in here it crosses 0, 0. So from negative 1 to negative 2, I want my slope to be 1 and cross the origin. From negative 1 to 2, my slope is 1. From negative 4 to negative 1, my slope is 2. So and then from 2 to 5, my slope is negative 1. So from 2 to 5, my graph is going down by 1s. So a sketch of our graph would look something like this. The slope from negative 4 to negative 1 is 2, right? We go over 1, up 2, over 1, up 2, over 1, up 2. Our slope from negative 1 to 2 is 1. We go up 1, over 1, up 1, over 1, up 1, over 1, and we pass through the origin. And then our slope from 2 to 5 is negative 1. We go down 1, over 1, down 1, over 1, down 1, over 1. you feel like you need some more practice on how to go from the derivative graph to the graph of the original, some exercises you can work on are 13 through 16 and 27 to 28 on pages 105 and 107 of your textbook. Take a second now and complete the bottom of this page. Where do you feel like you lie towards the objective? Are you on track or on a different train? If you feel like you're on a different train, again, go do some example problems so that you feel more comfortable with graphing. Okay, our last topic is going to be one-sided limits. But before we do one-sided limits, I want to bring your attention to the top of this page. So you will be needing to graph the derivative from data. Please refer to page 103 of your textbook. It has an example of graphing the derivative from data. The only reason I did not include this example in the notes is due to time. I did not want this video to exceed more than 25 minutes, and so if you refer to page 103 in your textbook, example 5 works through every single step necessary to graph the derivative from data. Okay, now on to one-sided limits. A function y equaling f of x is differentiable on the closed interval a to b if it has a derivative at every interior point of the interval, and if the limits from the right and from the left exist at the endpoints. In the right-hand derivative, h is positive and a plus h approaches a from the right. In the left-hand derivative, h is negative and b plus h approaches b from the left. The usual relationship between one-sided and two-sided limits holds true for derivatives. So if the function's right-hand and left-hand derivatives are defined, then the function has a derivative at that point, and it's equal to the left and right-hand derivatives. So let's do an example where one-sided derivatives can be different at the point. So we want to show that the function has a left-hand and a right-hand derivative at 0, but no derivative at 0. So in order to do that, we need to verify the existence of a left-hand derivative and verify the existence of a right-hand derivative. And if we want to prove that there is no derivative, then the left and the right cannot be equal to each other. So the left-hand derivative would be the derivative of x squared. So we have limit as h approaches 0 from the right of f of a plus h minus f of a all over h. So our a here is 0, because that is the point that we're looking at. So we want the limit h approaches 0 of f of 0 plus h minus f of 0 all over h, which is the limit as h approaches 0 of h squared, right? Because f of 0 plus h would mean that we're substituting h in for x squared. So we have h squared minus 0 squared all over h. Which is equal to the limit as h approaches 0. This would just be h squared over h, which reduces to just h over 1. And if we directly substitute, then our limit is equal to 0. Now to find our right-hand limit, we want the limit call from the left. I apologize for that. We want the limit as h approaches 0 from the right of f of b plus h minus f of b over h. So in this case, b and a are going to be the same number since we're looking at a point. So then we have the limit as h approaches 0 from the right, which would be our second function. So of f of 0 plus h minus f of 0 all over h. So the limit as h approaches 0 from the right. So this would just be f of h. So if we substitute h into our function, we have 2h minus f of 0, which would be 0, all over h. Which simplifies to the limit as h approaches 0 from the right. 2h divided by h is just 2. So the limit as h approaches 0 from the right is equal to 2. So the limit as h approaches 0 from the left of f of a plus h minus f of a all over h does not equal the limit as h approaches 0 from the right of f of b plus h minus f of b all over h. Therefore, f of x, f prime of 0 does not exist. Right, so if the derivative doesn't exist from the left and the derivative doesn't exist from the right, then the derivative at that point does not exist. So if you need more practice on these types of problems, complete exercises 31 to 32 on pages 107 of your textbook. We have now made it to the end of the notes, so if you could just take a second and fill out where do you feel like you fall with the objective of these notes. Have you met it? Are you on track? Are you on a different train? If you feel like you are on track or on a different train, feel free to go back and do some practice problems or jot down the information that you would like me to go over in class the next day.